You probably know who this guy is. I'm pretty sure you can guess it by the equation. He's George Ohm. In around 1827, he established this famous Ohm's law, which said that current through a conductor equals the potential difference across it. Now back then, we didn't know about electrons, but soon we discovered it around 1900s, and then people started asking the question, can we derive Ohm's law from the microscopic electron's point of view? Okay, and that's what you and I will do together, not in one video, but over a set of 3 or 4 videos. We will start from the microscopic version, looking at electrons, and we'll see how or why Ohm's law is true. What we'll do in this video is concentrate on the motion of the electrons inside a conductor, and we'll introduce the concept of drift velocity. So let's do that. Let me start by asking you a question. Consider a simple circuit with 5 amperes current through it. You might know that this current is caused due to the flow of electrons. And these electrons are flowing because they are being, say, attracted by the positive terminal of the battery. Now, my question is this. When something is being attracted, they accelerate, right? Just like when you drop a ball, it accelerates down due to gravity. It doesn't just flow down, it accelerates down. Similarly, these electrons must be accelerating towards the battery. Positive terminal of the battery, right? Accelerating. But if they are accelerating, doesn't that mean that they should become faster and faster as they go closer and closer to this positive terminal? And if that were to happen, wouldn't the current increase? Because current is the amount of charges flowing per second. If the electrons go faster over here, there should be more current over, more charges flowing per second, right? But we know that the current must be same everywhere in the circuit. So what's going on? What do you think is going on? How do you answer this question? Pause for a while and just wonder about this question and see if you can come up with some answer. All right, if you're giving it a try, here is the logic that I'm going with. So my logic was, without a battery, I know there is no current, so I'm assuming without a battery, electrons are at rest. And when I do put a battery, electrons start accelerating, and that's where it's causing a problem. So my assumption was, without a battery, electrons are at rest. I think that assumption is not correct. You see, just like how air particles can keep moving randomly without any breeze, these electrons are also moving randomly and with very high velocities without a battery. They are moving in all directions. So then why wouldn't we get a current without a battery? Well, that's because they're moving in all sorts of directions, and as a result, they don't go anywhere. Let me tell you what I mean. Let me just elaborate a little bit. Imagine we could zoom into this conductor. Okay, now here's an electron. Let's assume there is no battery right now. This electron will be moving with extremely high speeds in random directions. However, because there are these positive metallic ions, remember, metals have these electrons and these metallic ions. They will keep colliding with that metallic ions. The electrons will keep colliding, and as a result, they'll keep on bouncing randomly, and they don't get anywhere. They don't go anywhere. So for example, let's say that this electron is moving this way, randomly, in this direction. Then it bounces off this particular metallic ion, and then let's say it goes this way. And then again it bounces from here and goes this way. And again it bounces from here, it goes this way. And then it bounces from here and goes somewhere over here, let's say, and ends up like this. And because of this zigzaggy motion, the electron on a long time scale, if you look over a large time, the electron doesn't go anywhere, doesn't get anywhere. So here's how I like to visualize it. Look, the electron is moving randomly with very high speeds without a battery. But notice, it's pretty much in this spot. It's not moving anywhere. And all your electrons are doing the same thing. I'm just showing one of them. And this is the reason why we don't get any current. This random motion is extremely high speed, and it's caused due to the temperature, due to the heat energy. And that's why this is called thermal motion. So the thermal motion is very high speed, but it's randomly bouncing off, and on an average, the velocity is 0. And so it doesn't contribute to any current at all. Okay, so now comes the question, what happens when you do put a battery? What happens then? Well, now, because of the battery, the electrons will experience a force, and they will accelerate. So let's say the force would be in this direction. over here because they're being attracted by the positive charge of the battery. You can also think in terms of electric field, but as of now, it's not necessary. So it'll experience a force in this way. Now, as a result, the electron will now take a little different path. So because it is being accelerated towards the right, instead of bouncing from here, instead of going here, maybe it bounces off a little bit towards the right. This is the new path, okay? And then from here, it might, instead of bouncing over here, it will bounce somewhere over here. And then instead of bouncing from here, it goes somewhere here. And then it might go somewhere here. And then it might end up somewhere over here. And so what you now see is that in the presence of the electric field or in the battery, instead of ending up over here, the electron will end up a little bit to the right, a little bit to the right. And the same thing will keep happening. And as a result, now the electron will slowly and steadily start making its journey along the direction of that force. So it'll start moving in this direction. Again, let me show you this. Just like before, it's randomly moving, but this time notice it's slowly and steadily making its way along the direction of the force, along the conductor. We like to say the electron is now drifting. All the electrons will end up doing the same thing, and it's this motion that contributes to the electric current, this drift motion. And what's important is that this drift velocity, this average velocity that the electron has now acquired, is a constant. So let me write that down. These electrons are accelerating, yes, but they drift at constant velocity. This is the most important part to take away over here. So why are they on an average drifting at a constant velocity? Well, because see, the battery is accelerating them forward, but the collisions are decelerating them, and that balances out, and as a result, they end up moving with a constant velocity, the drift velocity. And of course, you may ask, how do we know that it's going to exactly balance out and remain a constant? That's something that we will derive in another video with great detail. We'll look at it mathematically. I don't want to do it over here and rush things. We'll do it slowly, and we'll actually see that this drift velocity is indeed a constant. And because it's a constant, and that's the reason why we'll have the same current in the circuit. And with this, you can now also understand where the energy from the battery goes. See, when the battery is accelerating the electrons, it gives the energy to the electrons, but then every time the electron goes and collides with these atoms, these ions, the electron transfers its energy to the ions, and the ions will now start vibrating. And this is the reason, as the ions are vibrating, we macroscopically tend to experience this as heat. And so we see the conductor heating up, and that's what happens, right? When you pass current through something, it heats up. Amazing, isn't it? So long story short, electrons have a very high thermal velocity traveling at hundreds of kilometers per second, but that doesn't get them anywhere. In the presence of a field or due to a battery, they now start drifting with a constant velocity called drift velocity that constitutes the current. And drift velocity is incredibly low. It's in the order of millimeters per second. All right, now before we close the video, to make sure that you really understood this, I want to ask you two questions, and I want you to pause and see if you can answer this question, okay? My first question is, imagine I increase the strength of the field. I maybe use a stronger battery and I increase the strength of the field. I want you to think about, under this condition, what happens to the thermal velocity, and what do you think will happen to the drift velocity? What will happen to these? Will they increase, decrease, or remain the same? Similarly, next, I keep the field the same, but I increase the temperature. Now what do you think will happen to the thermal velocity, and also what do you think will happen to the drift velocity? Can you pause for a while and think about this? Really think about this. You no need to use any formula based on what we just learned. All right, if you're giving it a try, let's see. Let's start with the thermal velocity. The thermal velocity was due to temperature. It's a random motion that is caused due to temperature, not due to the field or due to this force. And so in the first case, if I'm not changing the temperature, the thermal velocity will remain the same. So let me just say VT, thermal velocity remains the same. Okay, what do you think happens to the drift velocity? Well, notice because the field is stronger, I'll get more acceleration. The battery is pulling with more force, so more acceleration. So the accelerating force is more, has increased. What do you think will happen to the collisions? Well, notice that the thermal velocity remains the same, so their randomness remains the same, so their collisions pretty much remain the same. And therefore, the net effect is that the accelerating force has now increased a little bit. And as a result, you can kind of sort of see that now, yes, because the accelerating force has now increased, they will end up having a higher average velocity. And so the drift velocity would increase. You'll expect the electrons to go faster, and as a result, you'll have more current, which kind of makes sense. You'd expect stronger battery to get more current. Again, something that we will see in detail in another video where we'll derive an expression between the electric field and the drift current. So you'd expect the drift current to increase over here. All right, let's take the second case. In the second case, the temperature is increasing, so we would expect the thermal velocity to also increase. More temperature, more heat energy, and so it'll go faster. And so thermal velocity will increase. What do you think will happen to the drift velocity? Well, let's see. The accelerating force remains the same because I'm not changing the field now. However, because the thermal velocity has increased, because the random motion has increased, now there will be more collisions happening. Ooh, because of more collisions, I will have more retarding force, more, more opposing force. Yeah, that's the word I wanted to use. And as a result, because there's a stronger opposition because of more collisions, you can now kind of expect the drift velocity to become lower. And of course, you can stretch this and you can understand that that means that with an increase in temperature, your electrons will drift slower and the current will decrease. And that's indeed what we see. Again, something we'll look at later on when we talk about the thermal effects of electricity. That's pretty much it. I want to close this by saying that this model was first come up by a German physicist named Paul Drude, and so this is called the Drude model. And although the model is very primitive in the sense we are still using Newtonian mechanics, you might know by now that electrons are quantum particles and we need to use quantum mechanics. But even with Newtonian mechanics, we're getting a pretty good insight as to what's happening. And we will see, even with just this Newtonian mechanics, we will be able to derive Ohm's law.